Curie for having basically introducing already some of the basic concepts that I've scheduled to present here. So we'll be quite fast on the first slides. So just a small geographical presentation. I come from Italy, in particular from Sicily, that is the southern part of Italy, and from the province of Messina. This is the Strait of Messina, and where we have some beautiful artifacts, and in particular from the Institute for Chemical and Physical Processes. So let's go to the scientific part. I've planned to talk to students, so I've planned to give this lecture with an introductory part on vibrational spectroscopy, then introduce principles of surface enhanced Raman scattering source, and go deeper with wavelength dependence of the enhancement and field polarization in source and surface enhanced infrared absorption or scattering source. And then I will show you some application source for detection of pathology biomarkers. So let's go with the introduction of vibrational spectroscopy. What is vibrational spectroscopy? As you already know, this deals with spectroscopy, means interaction of light with matter, and with vibrational in the sense that we are not interested in the electronic states of molecules and or solids, but in their vibrational properties. You well know that you can do this in basically two kinds of ways. One is infrared spectroscopy, in which you perform absorption spectroscopy. You shine light in the infrared and you see what is transmitted. And so from what is missing, you see that, okay, it absorbed it, so it must have a special vibrational resonance at that energy. Otherwise, you can do vibrational spectroscopy in the visible range, using not absorption, but scattering, and in particular, what is called Raman scattering. Where does vibrations come from? From the fact that, as you know, matter is made of atoms and molecules, and atoms and molecules are not rigid, but they are always vibrating. Of course, you can approximate this with a spring. And so you have these resonant and vibrational energy levels that gives you specific absorption of specific scattering at specific energy levels. When you deal with molecules, you must think about normal modes, in the sense that each molecule that is made of atoms has 3 m degrees of freedom. Out of these 3 m degrees of freedom, 3 are rotational, all the molecule rotates. 3 are translational, all the molecule translate. So what is remaining is 3n minus 6 that are the fundamental vibrational modes. And with Raman and infrared spectroscopy, we get insight into the energy of these 3n minus 6 vibrational modes. And a clear example is of water. We have 3 atoms, so we have 3 vibrational modes. And the picture depicted below represents these vibrational modes that are the symmetrical stretching, asymmetrical stretching, and scissoring bending modes. Quantities and units. When we do spectroscopy in the visible range, we typically use nanometers, the wavelength of the light. Spectroscopy in the visible near infrared visible range goes from 400 to 700 nanometers. While when we explore the vibrations, of course the energy is much lower. It's much lower because at the denominator of the previous formula, you add the mass of the nucleus instead of the mass of the electron. And this makes lower vibrational energies, and the vibrational energies typically go into this range, means from what can I say, 1 millimeter, the low energy vibrational modes, to few, let's say, to few micrometers. Instead of using meters, we use reciprocal centimeters. The formula is like this, mu 1 over lambda, and this is much better suited. The reciprocal wavelength is much better suited to deal with this kind of problems. And just to keep in mind, 10 micrometers are equivalent to 1,000 centimeters to the minus 1. 2.5 microns are equivalent to 4,000 centimeters to the minus 1. There is a very simple formula that is mu in centimeters to minus 1 is 10 to the 7 over lambda in nanometers. So, energy levels. This is a typical Jablonski diagram of a molecule in which you have two electronic levels, n equal to 1. I'm sorry that this guy is not working properly. N equal to 1 and n equal to 2. The separation between these two big energy levels is in the visible or UV or very near infrared. Within each of these electronic states, we have vibrational states. These guys. And the energy of these transitions are, as we said, in the infrared range. And this deals with nuclear vibrations. So, as we said before, you can explore these energy levels with two techniques. One is infrared spectroscopy. You shine light at these energies, and if the energy matches the transition energy, then you have an absorption. So you need to work with thermal sources and detectors that are capable to detect thermal light. Otherwise, you can do it in the visible thanks to this guy, Raman. And how to do this? You exploit, instead of absorption, you exploit scattering. And how to model this in quantum mechanics? What typically happens is that your molecule is in the ground vibrational state. It can absorb a photon and go to a virtual energy state. It doesn't need to exist. It's just a visual energy state. From this point on, you can do the molecule can do different things. One is the electron can do different things. One is come back to its departure states. Then you have a photon, the emission of a photon whose energy is exactly the same of the one you shine. And this is called Rayleigh scattering. Matter diffuses light. This diffusion is typically Rayleigh scattering. What it can do is that the electron, instead of going into the molecule, instead of going into its ground state, goes into its first vibrational excited state. So this means that the photon that is emitted has an energy which is a little bit smaller than the photon that you shined. And the difference of energy between the energy shined and the energy that is scattered is exactly equal to the vibrational energy. So you can do a vibrational spectroscopy with visible light. Another thing that can happen, which is a little less probable, the one I was mentioning before is called Stokes-Raman scattering. Another thing that can happen is that the molecule is already in its V equal to 1, first excited vibrational state. So from this point on, it absorbs a photon of light, and when it goes back to the vibrational, to the ground state. In this case, the energy of the photon that is scattered is a little bit bigger than the light that has been absorbed. And in this case, we talk about anti-Stokes-Raman scattering. Again, the difference between these two energies corresponds to this vibrational state. The difference is, of course, as the professor before said, that the probability of these two processes are different, because the probability of having a molecule in the V equals 1 state is smaller, especially at very low temperatures, than the probability of having a molecule in its vibrational state, in its ground state. So you typically, when you do a Raman spectrum, you typically end up with this kind of spectrum, in which this very intense light is the Rayleigh scattering. You shine green light into silicon, you get out green light. This is Rayleigh scattering, and then you have these two inelastic processes that are Stokes-Raman scattering, in which you go to the vibrational state, you end up with V equal to 1. So the difference between this energy is exactly equal to this energy. We express in centimeters to the minus 1. For the case of silicon, one photon mode is 500 centimeters to the minus 1. And on the other side, you have the anti-Stokes, in which you are already in excited vibrational state, you go to virtual state, you go down to the ground state, and in this case, the energy is bigger than the photon energy. So we express it with a negative Raman shift, and okay. What basically these peaks tell us is that they are connected to, they can be used to detect analytes. Their position, their energy, and also their intensity are connected to composition, concentration, as we saw before, and so on and so forth. What is the basic? So this is a very beautiful and great techniques, very effective techniques. What are the drawbacks of this? The cross-section with respect to fluorescence. That can be several tens orders of magnitude smaller. So if even you have a minimum amount of residual fluorescence, this will cover all your Raman peaks, and you will not be able to do this analysis anymore. How to solve this problem? I mean, there are methods to improve this Raman spectroscopy, and of course they are related to the fact that we would like to improve the Raman scattering cross-sections. This can be done in an indirect way, that is using metallic nanoparticles and using the field enhancement process given by the localized surface plasmon resonance discussed before by metal nanoantennas. And this will give us rise to what is called surface enhanced Raman scattering. Why this name? Because the solution is the following. Instead of analyzing the molecule by itself, you first deposit it on a nanoantenna. I will call it nanoantenna because it amplifies as an antenna locally the field. And then the molecules undergo an enhanced field and that makes the Raman signal detectable. So the idea is to put molecules, bind them to nanoantennas, and exploit the localized surface plasmon resonances and field enhancement to improve the signal and make it visible. So let's go about a little bit some properties. So localized surface plasmons, I will not go into details because the previous speaker has already done it. The basic idea is that we use nanoantennas in which the field is, the electrons are confined, and there is a resonant process that gives us this expression of the local field. And as we already say, so if this condition is matched, this denominator increases, and so you have a strong field enhancement. Of course, in order to do this, you need materials that allow this condition to be fulfilled. And these, as we saw before, are silver, gold, copper, aluminum, in the different parts of the spectrum. We always prefer gold because it's very stable. There is much technology to fabricate gold nanoantennas and so on and so forth. How to detect these localized surface plasmon resonance is just a matter of doing absorption, extinction spectroscopy. You just shine light on the nanoparticle or on the nanoantenna and see what the detector sees after. Of course, what it detects is the sum of absorption plus scattering, whose photons are going away and are not detected. This is typically, in our experiments, is typically done, we do typically microscopy experiments. So we have the lamp, we shine the white light of the lamp, we collect the objective and send to the CCD. So from the experimental point of view, it's very simple. This condition, this one, is typically not exact for nanoparticles whose dimensions are 100 or 200 nanometers because of the fact that the nanoparticle will not feel a homogeneous field. As we saw before, we can apply the electrostatic model only if we assume that all the nanoparticles is feeling the same electromagnetic field. But since the electromagnetic field is oscillating and is varying into space, then we have to take into account this effect, and this effect typically broaden and redshift the localized surface plasmon resonance. And what typically happens is that the larger the nanoparticle, the more redshifted is the localized surface plasmon resonance. Another thing that is interesting, as was introduced before, is that if instead of using symmetric spherical nanoparticles, you go to spheroids or rods, you have different localized surface plasmon resonance due to the fact that this condition holds, and Lj is a geometrical factor. So if you take, as I will show you now, here, if you take, for example, nanoparticles, nanorods made by chemical procedures in water, you typically end up with this extinction spectrum in which this is the resonance along the long axis, which is larger, so it's more redshifted, and this is the resonance along the short axis. So cylindrical nanoparticles have two localized surface plasmon resonances instead of one. And okay, you can do it also with nanoparticles fabricated by electron beam lithography. In this case, instead of having an average, orientation on average, you can select the polarization, so you can select the long axis resonance, exciting with the polarization along the long axis, or you can excite the short axis resonance with the polarization along the short axis. Okay, what is also interesting is that if you, instead of taking small nanoparticles, you take longer and longer nanoparticles, or longer and longer nanoantennas, you will see the occurrence of multipolar resonance. It's like an antenna. If you take it longer, you have several conditions, several wavelengths that fulfill the resonance condition. And this is basically the same. What is again interesting is that if you take, for example, the dipolar resonance of the antenna, you have a field enhancement that is more pronounced than the edges. So the tips are the zones where the field is enhanced. If instead of considering the dipolar resonance, you take a higher order resonance, you start seeing zones in which the field is enhanced, also in the middle of the nanoantenna. These zones in which the field is enhanced, I will call them hotspots, because this is a current way to name these guys. Another thing is that, these are the resonances along the long axis, okay? If I excite this nanoantenna with a field along the short axis, I will have something like this. So you will see hotspots again, but the difference with comparison with before is that in this case, the hotspot is very confined, few nanometers, few tens of nanometers perhaps at the edges. If you excite this nanoline, this nanoantenna with a field that is polarized like that, you have an elongated hotspot. So in this case, the field enhancement is typically lower, but the fact that you enhance a larger area is of particular importance for molecular detection in cells, and we will see it later. So another thing that I would like to point out is that if you take a single nanoparticle, you will have typically two hotspots if you take the dipolar resonance and the edges. But if you take two nanoparticles and you approach them to get closer and closer and closer, you end up with one single hotspot at the nano-edge. So what typically happens is that the localized surface plasmon resonance shifts towards the red. You start seeing multipolar orders and so on and so forth. But what is important, I would like to point out here, is that instead of having two hotspots, you will have one nanocavity hotspot much more intense than the two hotspots. So it is convenient, instead of using individual nanoantennas, to couple the nanoantennas, because it amplifies more the field, and so it's much more effective for our detection purposes. So this is the physics that goes behind. Now let's see in a real SERS experiment what we are doing. So we take typically this cluster of nanoparticles, or these individual nanoparticles. Of course, they must have a localized surface plasmon resonance that we measure with extinction spectroscopy. Then the following thing is that we absorb the probe molecule, the molecule that we want to detect, on the surface. So one fundamental condition is that the molecule must attach to the nanoparticles. The second thing that we do is we shine with laser light. Of course, we want to exploit the localized surface plasmon resonance, so the energy of the laser must be within the resonance curve. In this way, we excite this collective oscillation of electrons that generates the hotspots. So the molecules that are located at the hotspots will feel an enhanced field. The local field felt by the molecules will be gamma times the field that we are shining. So this is the first part of the SERS. We are amplifying the probe field. Instead of 1 photon per second, the molecule will feel 100 photons per second. So we are amplifying the excitation field. But SERS is a scattering problem. It's a scattering process. So once the molecules scatter, if the energy of the scattered photons are again within the resonance bell, they will feel another enhancement process that will enhance. Sorry, you cannot see this. will enhance the Raman field by another factor, gamma rad, with respect to the Raman dipole that we would have in absence of the nanoantennas. So, at the end of the game, we have a twofold increase. The Raman spectroscopy is a two-photons process, and when you let the molecule interact with the nanoantenna, you have a twofold enhancement process. One enhances the excitation field, the laser field. The second one enhances the Raman field. And from the theoretical point of view, these two fields are treated in the same way. So, from the experimental point of view, what's the difference between a Raman spectrum and a SER spectrum? These two figures are the same scale, so you can compare these units with these units. We deposited methylene blue molecules, in the first case on a CIF2 substrate, glass substrate. Or the same results can be obtained if deposited on a globe flat substrate. So you see, these are 5 counts per second, let's say. If you deposit the same concentration of molecules on globe antennas and you excite them at resonance, you have this kind of signals. So in this case, you have 3 orders of magnitude. You can have several orders of magnitude. We discussed them. So a parameter that is important from the experimental point of view is the SERS enhancement factor. How much signal do I gain? And from the pure experimental point of view, this is given by the ratio between the intensity of the SERS with the intensity of the Raman. It means the intensity of the Raman signal that would have in absence of nanoantennas. For example, when I deposit the molecules on glass, on CF2, or on gold. Okay? This is affected, it can range 8, 10 orders of magnitude. There has been a strong debate, and there is still a strong debate on these numbers, out of which 2 orders of magnitude are typically are assumed to be done to the so-called chemical effect, in the sense that you have charge transfer between the molecule and the nanoparticles, and these create resonant states that can be excited, and so it provides some resonant effect. On the other side, all the rest, 6 to 8 orders of magnitude, are due to the electromagnetic effect, so to this localized surface plasmon resonance. So as I said before, the SERS is a 2-steps phenomenon in which we excite the nanoantenna amplifies the local field, then the molecules emit Raman photons, and the nanoantenna amplifies also the Raman photons. So you end up with a SERS gain that is given by the intensity of the local field divided the incident field, squared, of course, we are talking about intensity, and this also for the Raman photons. Since this gain is typically similar to this, we typically end up with an amplification that is proportional to the 4th power of the local field enhancement. Okay, so let's go a little bit in more detail, and let's afford this wavelength dependence of SERS enhancement. So we have seen that the Raman gain is given by this formula. These formulas do depend on the lambda. And of course, we want to know which, once we have our resonance curve, once we have our nanoantennas, which is the best excitation wavelength that provides the best Raman signal, the best SERS signal. And there was an hint that you can find in the paper of Moskowitz or this of Wokan that says that, okay, you get the maximum signal if the localized surface resonance is in the middle between lambda excitation and lambda F. What does it mean? That if you have your laser, you need to choose nanoantennas that are resonant in the middle, because this and this. And this is quite reasonable because you want to take advantage of the enhancement on the excitation and on the Raman, so you put it in the middle. The question is this true? We can do different experiments to check this, and basically we can do 2 different experiments. One is fixing the laser and changing the localized surface plasmon resonance. The other is fixing the localized surface plasmon resonance and scanning the laser. So, if you deal with nanoparticles that have this kind of diameters, size matters. In the sense that the localized surface plasmon resonance is shifted by several tens or even hundreds of nanometers. So, choosing the appropriate, if we have a fixed laser and a fixed molecule, choosing the appropriate diameter gives the appropriate localized surface resonance, and we look for the maximum enhancement. So, the group of Maclamide-Lachapelle has done 2 experiments, one in the visible, 633, and one in the near infrared, 785. And strangely, he found 2 different behaviors, in the sense that if we excite at 633, it turns out that source is maximum when lambda LSTR is in the middle between these 2 guys. So everything seems to work. But if we move to the near infrared, things are not so clear, in the sense that maximum enhancement was not obtained fulfilling this condition, but lambda excitation was less than lambda SPR. So this is not evident, and tell us that there are different behaviors at 633 and 785. Something is not yet well understood. Another parameter that is important is the fact that when we cover our nanantennas with probe molecules, the localized surface plasmon changes because of the different dielectric environment. So the question is, do we have to take into account this or not? There were experiments made by the group of Van Duyn that show that, yes, there is a shift in the resonance. They covered these nanantennas with benzene TO. And doing wavelength scanning experiment, they found that the maximum excitation wavelength is in the middle. So again, things are not clear, but experimental evidence is given. And what we did is doing some wavelength scanned source experiments for this kind of easy to fabricate nanoparticles. These are gold nanoparticles evaporated on glass. And they are near field coupled in the sense that the distance between the nanoparticles is in the 4 to 20 nanometers, so they talk to themselves. And okay, we absorbed methylene blue probe, and we performed extinction and source. From the extinction point of view, again, we see that when we deposit the molecule, the localized surface plasmon resonance redshifts. So we need to take this into account. But what was interesting is that if you look at this wavelength, we are almost out of resonance. But if we do source, and so here we are almost out of resonance, and here we should have maximum source, or quite big source. If we do the experiment, this is not true. We have maximum source at 785 and minimum source at 550. Gold is well known not to perform well in the green because the intraband resonances, the intraband transition absorb light. So we need to take this into account. What was again astonishing was that at 785 we had more intense source than at 633. And in order to clarify this, we used more laser excitations. So instead of 3, we used 7. We calculate the enhancement factor as the ratio of the source on the gold nanoparticles with respect to the Raman on a gold flat substrate. So whatever is connected to the chemistry between the molecule and the gold is already taken into account, because gold is here and gold is there. So the only thing that matters is the electromagnetic enhancement. And look at this plot of the enhancement factor. We have minimum enhancement at 515, a little bit larger enhancement at 532. We don't have absolutely maximum enhancement here, but we have larger and larger enhancement as we move to 785. So this is not something spare, but is well confirmed by this kind of curve. And again, I would like to tell you that we would have expected maximum source here around, but this is not the case. We have maximum source in the near infrared. And what is important is that in this case, the excitation, lambda excitation that provides maximum source is more than 107 nanometers redshifted with respect to the maximum of the localized surface plasmon resonance. Okay, I won't discuss this. Just a few words on the motivation of this. This is not the only result that has been achieved. Other groups have shown also this effect, and but not on these samples. And one of the possible explanations coming out now is that what we measure in the far field with extinction spectroscopy. So the information that we obtain in the localized surface plasmon resonance is not necessarily the same that holds in the near field. So it is like as in the near field, the resonance is redshifted. There are calculations. This is done by FDTD that shows that the near field resonance is redshifted with respect to the far field resonance. There is a beautiful, nice model based on the interpretation of the oscillator, harmonic oscillator, that gives this result. And what else? We are working also this from the experimental point of view. So this is an open topic, and there is another interesting paper published in PRL by the group of Aispurua and in Spain that shows experimentally that in the infrared 10 microns this holds. So I will conclude. So this part is concluded. From the field polarization inserts, I will extract only one part that deals with the importance of having the two resonances. I will not talk about polarization, we just talk about the fact that if, as we said before, elongated nanorods have two resonances. So we can think about using these nanoantennas, the same nanoantenna, to amplify both the source, the Raman, and the infrared. Okay, why? Because we can make very thin nanoantennas that are resonant in the visible along the short axis, and resonant in the infrared along the long axis. So we basically amplify this part, exploiting the long axis resonance, and we amplify this part, exploiting the short axis resonance. Let's see how. So there is an effect that was discovered in the 80s, Hunton, if I'm wrong, please correct me, that is surface enhanced infrared absorption. In the sense that if you deposit molecules on a rough metallic substrate, also the infrared part, so also the infrared vibrations are, the signal coming from the infrared vibrations is enhanced. What has been done in the group of Professor Pucci in Heidelberg is that they demonstrated this with nanoantennas. What's the advantage of the nanoantenna? With the nanoantennas changing the length, you can tune the resonance and so selectively enhance different modes. So these are antennas with different lengths. As you can see, you change the localized surface plasmon resonance, and in this case you enhance much more these modes than in this case. Okay? So by tuning the length, you selectively enhance some specific mode. So the idea is, okay, can we use individual nanoantennas to do surface enhanced Raman spectroscopy, and SARES, surface enhanced infrared scattering or absorption? It's not clear at the moment. What we did is, in the framework of the Nanoantenna European project, use these kind of samples. These are chains of individual nanoantennas. The width is 60 nanometers. We have a gap of 50 nanometers, but this doesn't matter because it's too large. So you can think about these antennas as individual nanoantennas. And the length was varied from 710 to 1910 nanometers. So we have antennas resonant in the infrared along the long axis. We have width of 60 nanometers, so the antenna is resonant in the visible along the short axis. And okay, we tried to deposit this methylene blue to see if it was possible to see the enhanced vibration in the infrared and the enhanced brown vibration in the visible. And this is a typical mixture of extinction spectra. This is the infrared part, where you see the plasmon resonances of nanoantennas of shorter and shorter length. Okay? The shorter nanoantenna gives higher energy localized surface plasmons. As far as you elongate an antenna, the surface plasmons cheat. And superimposed here, you see these enhanced infrared vibrations. And if you go to the visible, so these resonances occur for light polarized along the long axis. Okay? So you are monitoring the resonance along the long axis. If you polarize the light along the short axis, you have only one resonance at 641. So these samples are very well suited to do SARES here and SARES here, because you have resonance in the infrared and in the visible. What can be, let's say, simulated is the following. If we look at the long axis resonance, again, we see the two hotspots appearing at the edges. So, dipole resonance, hotspots appearing and very confining at the edge. If we switch the polarization from here to here and we pass from the infrared to the visible, then the hotspots get like this. So the resonance is less intense, but the hotspots is more elongated. You have, let's say, more room to put your molecules. Okay? This means that actually we can detect cells. How we can do it? We excited at 633 that was resonant with 641. With polarization along the short axis, you get this signal. As a cross-check, of course, you switch by 90 degrees the polarization. You excite with the same wavelength, but with polarization like this, and you get almost proper. You guess what I'm saying is that this signal is basically the same as the one that we get if we deposit the molecule on a flat gold surface. So it means that the nano antenna is not enhancing if the polarization is like this. And of course, this happens because the localized surface plasmon is not in the visible, but in the infrared. So, exploiting the short axis resonance, we can do SIRS. Exploiting the long axis resonance, we can do SAIRS. So, from these profiles, with a special data treatment that is a background subtraction, we obtain these signals, and these signals correspond to the infrared modes of metal and blue, while the signals here correspond to the Raman temperature. So the conclusion is that if you design properly nanoantennas, you can do surface enhanced Raman and surface enhanced infrared. You get this kind of enhancement factors when compared to the flat gold substrate. So we are very conservative. We don't want to normalize to strange things. And okay, let's see if we can apply this to molecular detection. I have just 5 minutes. I will concentrate on the main task of the nanoantenna project, that is selective detection of biomolecules. One of the most widely used method is enzyme-linked immunocytogenetics, assay. In the sense that you have your substrate, you want to selectively detect a protein, let's say, so you first functionalize your substrate with an antibody, then you bind your target, your antigen to the antibody, and then to detect these guys, you need a fluorescent probe. So there is a secondary antibody that is typically bound to a fluorescence molecule. So at this, you shine light. If you see the fluorescence, so this process has occurred, and you have the protein, otherwise not. Of course, what would you like to do is to stop here and see, okay, I don't want to use secondary antibodies and so on and so forth. I would like to detect this protein in a label-free fashion. How? Using Raman. Because, why? Because Raman, when I bind a protein to this antibody, I will see a Raman spectrum of the protein. Of course, the signal of the protein is too low. So the solution is using nanoantennas to do SIRS on functionalized nanoantennas to get the signal of the molecule. I won't comment on this. So what we were trying to do was to detect these two proteins, MNSOD and HEDNA1, that are responsible, that are biomarkers for a set of problems like ovarian carcinoma, sepsis, or lymphoma, and other kind of carcinomas. And the concept is that we use the nanoantenna concept. So we have the nanoantenna, we exploit the SIRS from the nanoantenna is functionalized suitably, and then, okay, we put in a solution with proteins, then we wash to remove what is not bound to the antibody, and then do SIRS. To do this, we have tried with these near-field coupled nanoantennas that, as I discussed before, provide maximum enhancement, working at 785 that provides smallest background. And okay, the procedure is basically like this. We have the nanoantennas fabricated by EBL, by the group of Enzo Di Fabrizio, former in EET in Genova. We clean with ozone. We then functionalize them with aptamers, DNA probes fabricated by the group at Biomagune of Valery Pavlov. So they are thiolated, so one side binds to the nanoantenna, the other side will bind to the protein. We use some blocking molecules to block the surface and avoid, as much as we can, unspecific binding of the protein to the nanantenna, and then functionalize with and then put the protein and wash. So, of course, at each step we want to be sure that nothing strange happens. So at each step we take cells. What happens is, if we take the bare nanantenna, we don't have any signal. We put DNA, we get cells of DNA. We put the 6-mercaptohexanol, and we still get the cells of DNA, but elongated, with the peaks that are broader. And then happens something strange, in the sense that if the nanantenna is not capable to enhance strongly the signal of the protein, we have basically a background signal that is the signal of DNA. But there are some specific sites, repeated several ways, in several points of the sample, that strongly enhance the signal of the protein. These peaks actually correspond to the peaks, to the vibrational peaks of the molecule that we have measured in solid. The same for EBDA1. The bottom one is DNA. This is the signal. No, sorry, I'm very sorry. So this is the upper. This is the protein. We can go down to 10 to minus 7. And of course, if we want to be selective, we need to prove this. We have made some preliminary tests with BSA. Instead of putting MNSOD, we just put BSA. And when we put BSA, we don't see the peaks of BSA. We just see the peaks of the background, means DNA plus 6-mercaptohexanol. So this helps us understanding that things go well. Okay, these are the conclusions. Basically, we're advancing to this nanobiosensor. I would like, in these last 3 minutes, I would like to introduce another way to detect biomolecules in liquid, and this is the following. Exploit optical forces. How to do this? You take your nanorods. In this case, they are synthesized chemically. You put in solution, in PBS solution with BSA, for example. If you take Raman of these guys, the amplification factor is not enough to provide cells of BSA. So you just see nothing. If, in other case, you start irradiating with laser light and you use this kind of sample chamber, you can push, by optical forces, all these nanorods toward the bottom, where they aggregate. So you pass from a condition of individual nanoparticle to a condition of coupled nanoparticles. And that's what we have been shown before. When you have coupled nanoparticles, the signal, the enhancer, the filament enhancer is much higher. And this, as I will show you, provides cells from the molecules that are lying in the hotspots. So this is a movie in which we shine and we observe, and we see the nanoparticles passing and being pushed down. So it passes through the laser spot, and is pushing down, is pushed down, is pushed down. At the end, after some seconds or minutes, depending on the conditions, you get this sort of aggregate. This aggregate contains nanorods, BSA, PBS, and the surfactants. What we get is that as a function of time, at the beginning we don't see anything, then we start seeing stronger and stronger and stronger signal. In the case, if we focus on the phenylalanine ring of BSA, we see that before we had just the signal of PBS, the buffer, then this peak goes up, 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 and the same occurs on the CH. So what typically we end up is the following. Cells of BSA at concentration of 0.1 picomolar. This is particularly an interesting factor because if you try to do Raman on BSA in PBS, you don't see, you won't see anything at 0.1 millimolar. Just have the peaks of BSA. You can repeat this experiment with lysozyme, phenylalanine, and manganese oxide dismutase and see again this kind of process. So I would like to just acknowledge the people that have been collaborating at IPCF in particular Barbara Fazio and the PhD student Cristiano D'Andrea, and Francesco Bonaccorso, who worked also on the polarization but is now involved, and you will hear him in the next few days talking on graphene. And the project that followed this, that is the Italian PRIM project and the Nanotera European project, and these are all the collaborators from the several groups in Italy. And okay, thank you very much.
Thank you very much for your lecture. Any question? Based on my question. Okay.
So, thank you very much for that excellent talk. I just want to ask you, why you say that nanoparticles, this rods migrate under the laser spot. What is the reason why they migrate?
Optical forces. When you
and this,
have you heard about optical trapping?
Mm-hmm.
Okay. In optical trapping, you have a microparticle that is trapped in the laser spot because the balance of the forces is so that the particle is attracted in the spot. Okay? If the refractive index is not good enough, there will be no trapping but expulsion. So the laser, the light will interact with the nanoparticle, will transfer its momentum to the nanoparticle, so the nanoparticle will either be trapped or push it. Okay? And it can also rotate, but this is not the case. We will not afford this. So, in our case, we were red shifted, we were blue shifted with respect to the LSPR, and this is a condition that is known to give rise to repulsive forces. So the nanoparticle passes the spot, receives the photons, receives the momentum, and goes down. When the nanoparticle is coated with this protein, it goes toward the glass, and toward the glass there is a sort of sticking. So the first nanoparticle sticks to glass, the second nanoparticle to glass and to the nanoparticle. So you create this aggregate by means of this optical force and this sticking phenomenon. And when you have aggregate, you have strong cells. Actually, I can tell you something. We are struggling a lot with using these nano antennas and so on and so forth. But from the experimental point of view, the most signal you get when you have rough stuff, whose resonance perhaps is not well matched or not well established, but rough gold gives 1 or 2 orders of magnitude more signal of gold, of nanoantennas and so on and so forth. But okay, if you engineer the localized plasmon resonance, you can do these strange sales experiments.
Okay. Thank you. Have some young people have some questions? Not only professors?
can I ask one small?
You are
You mentioned far field resonance and near field resonance. What is the difference? Can you say?
It's still under, it's, like to say is, if you instead of considering the local density of states that you see in the far, I will start from the beginning. Far field light is, in far field light, the field is transversal. In near field, the field is not necessarily transversal, but can be longitudinal. This information is lost in the far field, in the sense that what you get in the far field only refers to this transversal part of the field. What is, for the moment, taught is that if instead of measuring in the far field, you would have been capable to measure in the near field, as with SNOM or things like that, you would be sensitive also to the contribution of these, not transversal, parallel components of the field. And these components of these longitudinal components of the field are actually redshifted with respect to the transverse components. And this seems to be the physical reason. The transverse components have a different spectral distribution of the longitudinal components. But this is under...
Unfortunately, we should finish the discussion. Thank you again for your lecture.
Thank you again.